Hello, welcome back to Chemical Engineering 2100. This is Dr. Christy Patton-Lukes, and we're going to begin talking about material balances. So Chapter 4, it's called The Fundamentals of Material Balances, and really this one chapter, if nothing else, is the one thing that you should try to become perfect at. This will make a huge difference in your entire career as a chemical engineer. This is the most fundamental thing that differentiates chemical engineers from other types of engineers. So what we're talking about here is really very, very simple, yet it does require practice. So basically, if you have a material that enters a system, whatever that system might be, maybe it's a bowl to make cookie dough, okay, and you put that material into the system, it's either going to come back out of the system, it's going to stay in the system, or it's going to turn into something else. For our purposes, that turning into something else will happen by reaction. What we'll be doing in this chapter is learning how to quantify all of this. So, processes. We're going to want to be able to classify processes because that will make solutions easier. Typically, we're going to call them either a batch process or a continuous process. And then we'll have this other weird category that is the semi-batch. A batch process is one where you have a certain amount of material already there. That's the starting point. And then you do something to it, and then you have material at the end. Okay? And so that's a batch. You have something, a starting time and an ending time. A continuous process is more likely to look at a piece of maybe equipment. Okay, you have steady flow of feed into this piece of equipment, and then you have a flow of material coming out. The process is what's going on between the inlet and the outlet. Now this could be steady state so that it continues to be the same all the time. It could be something where the flow rates change over time. Our third category is the one that is, it's a blend of the other two. You know, some things are kind of like batch and kind of like continuous. You have flow in and out, but it's not really steady. There was already some stuff there at the beginning, and then things are different later in the process. These are kind of like if you're filling up a bathtub. Okay, you've got flow coming in, but you also have material that's accumulating inside the system. Okay. Semi-batch systems are going to somewhat be a combination of the batch and the continuous. You're talking about beginning and ending time, but you're also talking about flow in or out of the system. So let's talk about doing material balances and see how that relates to these process classifications. So really what we're talking about, no matter whether it's batch or continuous, is we can sort of draw this with a very simple block diagram, okay, where the process, whatever that process might be, it might be a pump, it might be a heater, it might be a reactor, it might be a cookie bowl, okay, but you have feed that goes in there, and then you have a product that comes out at the end. And even though this looks like it has flow, this actually can be very nicely adapted to the feed is what was in there at time 1, and the product is what is there at time 2. A material balance basically says, well, this is the generic way we write a balance. Input plus generation minus output minus consumption is what accumulates. So the feed is the input, the product is the output. The generation and consumption are going to be the pieces that deal with reactions. Generation is created by reaction, consumption is used up by reaction. The accumulation is the piece that is the net change inside the process. So maybe you're filling something or draining something, or something is leaking, or something is being absorbed onto a surface somehow. Okay, whatever the technique is, the accumulation is going to be a change in mass over a period of time. So let's look at 3 special cases. The first special case is the one that seems to adequately describe so many processes, and it turns out to be fairly easy. Okay, we have a continuous steady state process. There's no change over time if it is steady state. If there's no change over time, then you cannot have accumulation. Accumulation, just by its definition, means that there's change happening over time. So the balance is just input plus generation minus output minus consumption equals 0, or it's much easier if you say input and generation are equal to output and consumption. So we have the in equals the out, and then we also have the reaction component here. Of course, if I don't have a reaction, special case number 2, this is even easier. So I have a steady state in and out, no accumulation because it's steady state, so no change with time, and there's no reaction, so I get rid of the generation and consumption term. So I end up with just the very, very simplest, input equals output. Then of course we have those batch problems. For a batch problem, we're going to have no flow, so the input and output are going to be 0. So we're left with generation is equal to consumption plus accumulation. Again, we can deal with this very many different ways, but one way to deal with the accumulation is it's simply the change between the beginning time and the final time, correct? If you have a differential equation model, then you could actually write this as a differential equation and solve that. But most of the time, we can just simply look at this as the difference. So what was in there at the beginning, what was in there at the end. And if you do that, then we have that the initial plus the generation is equal to the final plus the consumption. If you treat the initial as an input and the final as an output, then this equation looks very, very similar to the steady state. But remember, these are not systems of flow. For the semi-batch, we have to go back to the original equation. And we'll do a few of these examples of these various sorts in the next several lessons.